Good morning, good afternoon, or good evening. Welcome back to the walkthrough of the Step 2 2024 paper. And we've got ourselves to question number 8. As always with these, I haven't seen the question beforehand. This is as close to a blind walkthrough of these as possible. And if you're having an attempt at these yourselves, please do have a go before you start watching the video, and only come to the video either when you've completed the question and you're looking for some more insight into what it's going on about, or you've had a go, you've got stuck, you've persisted with being stuck, and you need a hint. Of course, when you get that hint, please do pause the video and carry on attempting yourself. Otherwise, you lose a huge majority of the value of working through these questions. So let's have a look at question 8. Quite a long question. It's covering the whole page, and it starts with a theorem. Let U1, U2 be a sequence of numbers if the sequence is bounded above, i.e. every term is smaller than some fixed value, and it's increasing, then there is a number L less than or equal to that bounded above value, such that the UN tend towards that L as n tends to infinity. This is actually an incredibly powerful theorem that is introduced very early in a first course of analysis. This is the bounded convergence theorem. If you've got a bounded above and you're monotonic, i.e. you always are increasing or always decreasing, then you have a limit. So we're going to probably try and use this theorem multiple times in this question. We've then defined a couple of functions. For any real numbers, x and y, we're going to define a of x, y to be half the sum. It'd be interesting to know why they've called it a. Normally our functions are f, g, h, but this is our arithmetic mean. Add them together, divide by how many. If there's only 2 of them, you add together and divide by 2. So this a of y is the arithmetic mean, and then g of x, y, we're going to multiply and then square root. Very similar concept, at least. Instead of adding, we're multiplying. Instead of dividing, we're rooting. The g here is actually the geometric mean. So we've got 2 ways to find the mean of 2 values defined by these functions. We're going to have an x0 and a y0 be some starting values, with the x0 being the larger. And then we're defining a sequence where each of the x's are the arithmetic mean of the previous 2, and the y's are the geometric mean of the previous 2. Quite a classic, actually, question 8 in these step papers. Question 8 quite typically is, here's a concept which is completely alien to you, but is quite a common university style topic. Can you work out how to use it? So jumping straight in then to the actual question, 8 part I. It's telling us what to think about. It's telling us to consider this root xn minus root yn to try and show that yn plus 1 is less than xn plus 1. So let's see exactly what this, how this is going to help us. Well, the first thing to notice, and is what I'm going to reference straight away, is this is greater than or equal to 0. Whenever we square a number, it gives a positive solution, certainly for real numbers, and we are in the real world here. So as a square is non-negative. Now, the only thing I'm a little worried about here is the final answer is a strict inequality, whereas this is a less than or equal to, provided that xn is not equal to yn. Maybe I need to justify that in a moment. That feels quite difficult to justify. But expanding this out and seeing what happens, this is going to be xn minus 2 lots of root xn yn plus yn greater than or equal to 0. If I rearrange this to make it look like the functions that I have been told to think about, I'm going to, let's make sure we get things on the right sides. Let's keep the xn and yn on the left. Let's send the roots to the other side. Apologies. And let's divide by the 2. So then the left side is the xn plus 1. And the right side is the yn plus 1 by exactly the definitions given. So, why is this a strict inequality? And it's going to be a strict provided that xn is not equal to yn. Now, my instinct is to do an induction style step, because we have that y0 is less than x0, which will then mean that y1 is less than x1, and then etc, etc, by following this exact argument. But that's induction, and step 2 officially doesn't need further maths ideas. And I think I might still have to do it though, as x0 is greater than y0, that's going to imply that x1 is greater than y1. I should probably put the comments up on the previous line with equality only if xn equals yn. The only way for a square number to be equal to 0 is if you are squaring 0 itself, which implies x2 is greater than y2, ... which is going to mean that xn is greater than yn. So therefore we don't have the equality case, xn plus 1 is greater than yn plus 1. I've kind of done a poor man's induction there to get the result that they wanted. Okay, show further. We want to show that xn plus 1 is less than xn. Well, now we have xn plus 1 is defined to be half the sum of the previous, but we know that this is less than half xn plus xn. Let's just say for all n up here. Okay, but that's exactly what we wanted. I have just used the previous result there, that the xn is bigger than the yn. So this is equal to xn, as required. And if we try and do the same thing, let's go for yn plus 1 is equal to the root of xn yn. Now this time I want it to be the other way around, so this is actually going to be greater than root of yn because the x's are bigger than the y's, so if I replace it with y, I'm getting smaller, but that is equal to just yn as required. Okay, nice. So we have some sequences here. In particular, we have that the yn sequence is increasing. The xn sequence is going to be decreasing, and as kind of mentioned at the beginning, that the theorem at the top does work for decreasing as well as increasing. But now we actually want to use this theorem to deduce that there's a value of m such that yn tends towards. So we've shown we have that yn is less than yn plus 1, which and we kind of want to show this is less than some fixed value as well to use the theorem. So this is kind of the second bullet point of the given theorem. So this is less than, well, the x's are bigger. So this is less than xn plus 1. But xn plus 1, well, bigger than that is the xn. That was the first bullet point. But then bigger than that has to be the xn minus 1 all the way. So the x's are a decreasing sequence. So actually, for all n, so yn is bounded above by x0. And that x0 can take that role of the b in the definition of, in the condition for this convergence. So then, thus, there exists an m. Now, in the thing it said the m is less than or equal to the bounding value b that we made. So this is definitely less than or equal to x0, such that yn tends towards m as n tends towards infinity. So we found an upper bound. We showed that it was a increasing sequence. So the theorem tells us that there is a limit. Okay, carrying on then. Show that 0 is less than, so certainly xn plus 1 minus yn plus 1 is greater than, or the x's are bigger, is greater than yn plus 1 minus yn plus 1. I've made that smaller equals 0. So certainly this thing is bigger than 0. So that's one side of it. And the other side. So how am I going to show that other side? And, well, I could do the inequality on xn plus 1 minus yn plus 1. Now, if I replace the yn plus 1, because it's a negative yn plus 1, I'll get the same condition. It'll be greater than the xn plus 1 minus xn plus 1. So, why does that end up working? Well, we can try and use the definitions. I'm feeling like there's something a bit more pleasant going on. But there might not be. It might just mean I need to use the definitions and just deal with it. I can't. I'm just going to use the definitions and hope something happens. I might accidentally reprove something I've already done. If I want to show this is less than something, I could use the fact that the xn plus 1 is less than xn, but then yn plus 1. Yeah, using these two conditions, the xn plus 1 is less than xn, and this one, of course, the yn is a negative, I will get that this is less than xn minus yn, but I want it to be less than half of it, not just less than the difference. So those conditions aren't actually strong enough to get the result I want, which then doubles down on the fact that I think I just have to use the definitions. So this is a half xn plus yn plus the root of xn yn. So that's just using the definitions of xn plus 1 yn plus 1. And I want to be making this smaller. So, sorry, I want to be making this bigger. Oh, I've got a sign error there. Let's change that to a minus. So this is going to be this thing minus. If I want to make this bigger, then I can do this as subtract a smaller thing. Well, a smaller thing is the yn. The x's are bigger than the y's. Well, then that's going to be a half xn plus a half yn minus an entire copy of yn, which gives exactly the xn minus yn, half of. Okay, well, I can iterate this, and then this thing is going to be less than a quarter xn minus 1 minus yn minus 1, less than an eighth, etc., less than, all the way back up to the initial values. So, well, is this going to be just another application of the original theorem? And it looks like it might be. So first notice, and let's call it, just check it hasn't been used later in the question. Nope, let's say Zn. Let's call this the difference between them. Then Zn plus 1 is less than, actually, I want to be able to use the theorem exactly. And the theorem's been quoted for increasing. So I really want this to be a decreasing sequence. So I'm going to call it yn minus xn. Then Zn plus 1 is negative xn plus 1 minus yn plus 1 is not going to be less than, it's going to be more than negative a half xn. Once you swap the sign, you swap the inequality direction, and that's equal to the half Zn but that's not necessarily decreasing though, because of this half now is, sorry, increasing. Or I think I could probably just do this in a much simpler way. Rather than trying to forcibly use the theorem, let's do, as I was mentioning earlier, and iterate this procedure. So the xn plus 1 minus yn plus 1 is going to be less than a half, which is going to be less than a quarter, which is going to be dot less than 1 over 2. Now I'm going to think about that power x0 minus y0. How many steps have I done? I've had to do n plus 1 steps to get all the way down. So it's going to be less than 1 over 2 n plus 1 of a fixed value. x0 minus y0 is a known fixed value. But this thing tends to 0 as n tends to infinity. Thus, xn plus 1 as n tends to infinity is bounded above and below by 0. That means that xn plus 1 minus yn plus 1 has to actually tend to 0. Its upper limit is getting smaller and smaller and smaller. Its lower limit is 0, so it has to tend towards 0 at the end. Okay. So therefore, we can say something about xn. Therefore, what's the best way to say this? Because this thing is clearly saying that in the limit, xn equals yn. Now, do I want to be more formal? And this is kind of the difference between analysis at a university level and maybe what this question is requiring of us. Therefore, xn plus 1 and yn plus 1 to the same value, i.e. xn tends to m as n tends to infinity. And if you want to look up how to formalize that, there are epsilon arguments or epsilon methods, which are fascinating and lead to some fabulous, both painfully fabulous arguments. But every single one of these proofs starts with let epsilon be a small positive value, leading to probably my favourite joke of all time, let epsilon be negative. And that is inexplicably hilarious to mathematicians who have spent some time doing analysis. Hey, that's part I done then. So part double I. How is this all going to relate? Now we actually have an integral where we have some positive values, positive real numbers going into an integral of that form. So this does not look like a pleasant integral. Straight away it's giving me vibes of inverse trig, that square root of 1 over the square root of something squared plus something squared is very common in the inverse trig integrals. But because there's two of them smashed together, maybe it's a partial fraction. Maybe I can get that involved. Now, partial fraction with square roots in, not a normal. But maybe something can come up. Now, luckily, the question is telling us how to actually proceed. It's telling us to use a particular substitution. Now, that substitution didn't really fit with the ideas I was quoting there, but let's see what happens. So let t equal a half x minus pq over x. So this is going to be some really clever substitution that's going to fix a lot of our problems. And if we look at what the solution is, this component here is completely... no, they're both in terms of t, aren't they? T is now the variable. So it's changed it in some way, which maybe is helpful. And we can kind of see what's going on in the final parts of the question, actually linking it back. So let's go for, so we need dt by dx. If we differentiate this, we're going to get a half. That's really an x to the minus 1. That's going to be 1 plus pq over x squared. Do that differentiation slower if you need to. So then, and that's not really pleasant at all, that's going to give, and I don't really like using this notation, but it is going to help us out here a little bit. The dx is going to be equal to 2 over 1 plus pq over x squared dt. So that's telling me how my substitution's going on. And then when x is infinity, which is a really awkward thing to say, really I'm thinking as t tends to infinity, and maybe I should actually be that formal. As x tends to infinity, t is going to tend to, well, the fractiony bit, this is going to tend to 0. 1 over a huge number, anything over a huge number goes to 0. And the x bit at the front is going to tend to infinity. Half of infinity is still just infinity. So that limit is going to go to infinity. And as x tends to 0, and again, I have to use the tends to because I can't sub-0 into this substitution. Now it's this part that goes to 0 and this part which goes to infinity, but now that's a negative infinity. T goes to negative infinity. So I've dealt with the variable bit, the dx term, and I've dealt with the limits. So now this can start to be manipulated. So this is going to be equal to the integral between negative infinity and infinity of, now writing it is going to be quite awkward. And actually this thing is really awkward to make the substitution on. It's going to be really, really awkward. So maybe I want to do more manipulation to this statement before I try and sub it in. Because I need to substitute in an x squared rather than a t, whereas this is written as t equals. So how am I going to do that? Let's bring this down and start playing with it. So this is going to mean that 2t, I really want to write it as x squared equals. So I really do want to multiply through by x, but I also don't want to do that at the same time, because I'm going to have a 2tx equals x squared minus pq. So that is telling me what x squared is, but it's still in terms of x. And even this thing over here, I should probably manipulate a little bit more now, knowing that things are going to be so awkward. So I'm going to multiply up and down by the... I've just lost the screen share there. Let me bring that back. Try to bring that back. There we go. Hopefully I spotted that straight away. So because it's so unpleasant, it just is really unpleasant. So how am I going to manipulate this into a way where I can get x squared as the useful aspect? Because I do certainly have... I wasn't on the eraser. So this does say that x squared equals 2tx plus pq. But if I sub that in, I don't think I'm getting something particularly useful. Now, that doesn't mean I shouldn't just try it and see what happens. I'm just looking for any magical things before I just go straight for it. Because I don't really... If I sub it into this term here, I'm going to have t's and x's all over the place. And I really want to get rid of all the x's in one go. Now, I do also have the opportunity to complete the square on this and see what happens if you ever have a quadratic in x squared. Sorry, a quadratic in x, then completing the square is a good way to get just the x on its own. The awkward thing is going to be, I will then need the square root to isolate this x. Let me just check I've done that correctly. I've had to add a t squared to both sides to complete the square. So this does tell me what x equals. It's really unpleasant. X would equal, and unfortunately it does have a plus or minus in it, t plus or minus the square root of t squared plus pq. And if I do square this, because I'm substituting in an x squared, it's going to get even worse. I'm going to write it out and hope. This is going to be t squared plus or minus 2 lots of, and then it's always going to be plus t squared plus pq. So I can again simplify that a little bit. But if I'm subbing that in, it does not look like I'm getting what I want. Not even close. Now, another thing to be slightly, maybe not worried about, but in this condition here, and the original integral, P and Q are both symmetric, but it appears that, or maybe one of the brackets is going to do one thing, whereas the other bracket does something slightly different. Which is a little bit awkward. We don't really want symmetric things to be asymmetric. So, my next worry is, have I made some kind of silly error somewhere? Quite possible with algebra like this that a slip will happen. So I'm just going to go back through, check that one, I've written things down from the question correctly, and two, any techniques I've applied have actually been correct. So I'm first going to check if I do differentiate this. If I write it out properly, do it a little bit slower than I did the first time, I do get the half, and I am going to get a plus half pqx to the minus 2, which is indeed what I've got there. The dx and multiplied back over is giving me that thing. Now, do I need to be worried because I have something here? Now, one thing we can spot is these two things are kind of dots of each other if they do end up smashing together. Now, do I want an x to the power 4? Probably not. I feel like it's got to the point where I just need to smash it into the integral and see what happens. So I'm going to continue over here so I can hopefully keep as much as possible on the screen. So we now have that this thing is going to be equal to the integral between negative infinity and infinity. I still don't know how I want to sub this in, because I need to write this thing in some way. Now I could replace the x squared with this thing here. Now that plus p squared, doesn't look like it does anything nice. Unless the question's implying I should be doing this whole thing the other way round. Instead of going from the dx integral into the dt integral, let's go from the dt integral back to the dx integral. Because then things are going to be more so the right way round. So I'm actually going to try that. And I'm going to do that in a bit of a fresh space. So instead, let's consider the integral between negative infinity and infinity of a quarter p plus q squared. Let's try and write that slightly nicer. Plus t squared and pq plus t squared, all square rooted, 1 over dt, and let t equal the half x minus px over q. And if we do read the question actually really carefully, this is what the question's telling us to do. Use the substitution in that integral to show something. So let's do it. So now dt again, dt by dx, and that's going to be a more pleasant way round as well. It's going to be half of 1 plus pq over x squared, which then can give some quite nice stuff. Now we do need t squared, and let's actually work that out. So t squared is going to be equal to a quarter, and that's going to be x squared. If I multiply them together, it's minus 2pq. The x's are cancelled out the middle term, plus p squared q squared over x squared. I'm going to call this integral up here j so I can reference it. Then this j, oh, I should do the limits as well. And that's the same as before. As t goes to infinity, the x has to go to infinity. As t goes to negative infinity, x goes to 0. That's exactly the same arguments we had on the other side, now in reverse. It's now going to be integral between infinity and 0 of a half 1 plus pq over x squared dx over the square root of a quarter p plus q squared plus that thing. Benefit of doing it on the screen, we can zoom in slightly, plus a quarter x squared minus a half pq. I'm expanding this out, and I probably should have expanded the other section out as well, knowing that I'm hoping to do a lot of simplification. And then the other term is pq plus the same thing, quarter x squared minus 2pq plus, and again, I've not really expanded that bracket out there correctly. That's minus a half pq plus p squared q squared over 4x squared. So now we just need to manipulate and hope. So this is now still integral between 0 and infinity. Numerator I don't think I want to touch just yet. X squared. Now the denominator. These brackets we're going to have to hope do something magical. So we've got, it's all under a square root. And we have, slightly worrying that the x squareds aren't just immediately going to disappear. Again, I'm wanting a nicer way to do this, but I'm not seeing it. So a quarter p squared plus a half pq plus a quarter q squared plus the quarter x squared minus a half pq. Oh, there's something that cancels. I've lost a 4 on that term. So that's my first bracket. This unfortunately now is just algebraic unpleasantries. Those cancel. Now I'm aiming for this bracket to either be p squared plus x squared or q squared plus x squared. And this looks like it's neither still. Even with some cancellation of the numerator term. I'm already thinking that this x squared and this half is going to come into the denominator to help me out. Now this other one also doesn't do anything too exciting. It's a quarter x squared plus now a half. Now this one does do something a bit more exciting because that's factorizable. Those three terms is now just exactly this, but with the sign in the middle swapped. So we can write that as something squared. Does that help? Don't know. I still haven't got my dx on the end, so let's put that in. So now I think I want to start dealing with the unpleasantness in the numerator. So I'm going to put a 2x squared down into the denominator. And I think I want to put it under the square root. So that means I've got I've got 2x squared times 2x squared, which means I can put a 2x squared into both of the two brackets, kind of double dipping on it. So this is going to be the numerator, if I'm timesing top and bottom by x squared, will be an x squared plus pq. The denominator, so it's the square root of, and now I'm going to put a 2x squared into both. I've still got the halves there. Do I want... I kind of want to put 4x squared into both. Can I manage to put 4x squared into both? So that means I need to times the denominator. I want to have a 4x squared, which is really just a 2x on the outside. Let's try and be really clear with what I'm doing. So I'm multiplying the numerator by 2x squared. So I'm going to times this bracket, which means I need times the whole denominator by 4x4 when it goes under the square root. So I want to times this bit by 4x squared, and I want to times this bit by 4x squared. So I actually need to times the numerator by 4x squared. So the numerator's got an extra factor of 2, which hopefully will cancel out later. I can deal with a factor of 2, hopefully, at another time. So let's actually do that down in the denominator. So in the denominator here is going to be p squared x squared plus q squared x squared plus x4 plus p squared x squared. And that still doesn't look very nice at all. But maybe, if I'm looking, yeah, still don't like the look of that. The second one is going to be x to the 4 plus 2pq x squared plus p squared x squared. I've lost the squared on that p. dx. I was hoping that these denominators would factorize really pleasantly. And now I'm getting more worried about that 2 as well. So square root of. Now that second bracket, I know I can factorize that second bracket quite nicely. But the first? Oh, the first gives me an x squared plus p squared, x squared plus q squared. If you do FOIL that back out, you do get exactly that set of algebra. And now the second one is x squared plus pq times x squared plus pq dx. But this is now exactly what we wanted, because these two, once square rooted, is exactly what's on the top. So this thing cancels with those two simultaneously. And now to worry about this 2. So why, oh why, is there an extra 2? I don't, oh, the extra 2 is probably to deal with these limits in a moment. Okay, so this thing is now equal to the integral between 0 and infinity of 2 over the square root of x squared plus p squared, x squared plus q squared over dx. So this is equal to 2 lots of what was defined as IPQ all the way back on the previous page. But also J is going to be equal to. So now I want to write J in terms of the IPQ stuff. So J is going to be, or is, the integral between negative infinity and infinity. And this is where these double limits, I think, are going to help us out. So this is over the square root of, and notice the quarter p plus q squared is exactly a of pq squared plus t squared. And the pq can be written as the g of pq squared, that gets rid of the square root in the definition, dt. But notice that this integrand is even. The positives and negatives do exactly the same thing. So this is going to be equal to, I should probably comment that rather than just stating it, the integrand is even. An even function is where you sub in a negative, you get the same as if you sub in a positive, which means the integral between negative infinity to infinity is really just 2 lots of the integral, and I'm really abusing notation here, between 0 and infinity. So this is going to be equal to 2 lots of the integral between 0 and infinity of all this junk, which is 2 lots of I APQ GPQ. Which means that if I put those two results together by calculating J in these two different ways, I get the required statement. Quite a common technique. Pick something completely, well, not completely random, but something completely different to evaluate, to link what you actually care about as required. Okay, so we now want I of x naught, y naught. So now I of x naught, y naught, well, that's equal to, by the statement directly above, a of x naught, y naught, but that's exactly x1, and g of x naught, y naught, which is exactly y1, which equals which equals I of xn, yn, by repeatedly applying that statement we just have, which tends towards, and we should argue about, does the x naught and y naught tending to something imply that the integral of some combination of them tends to the same thing? Debatable. Something that an analysis course at university would do, but we're not worrying too much about convergence problems here. But now we've got this I of mm, which is equal to the integral between 0 and infinity. And if I replace both p and q with m, the integral becomes 1 over m squared plus x squared dx. And now this is what the vibes were giving right at the very start of the integral part of this. I'm just pulling up the formula sheet so I make sure I pick out the right one. This is an inverse trig integral. Now I'm pretty sure this is tan inverse. Yep. But with that extra m, we need to be a little bit careful. So it's that statement there. So this is going to be tan inverse of x over m, and there's a 1 over m in front between the limits of infinity and 0. So tan inverse of infinity is pi by 2. That's going to be pi over 2m. Tan inverse of 0 is just 0. So I of x naught y naught is equal to pi over 2m, m being the limit of these xn sequence. Quite a fantastic way to evaluate this integral by first creating a sequence showing that this integral is invariant along the sequence, and then evaluating the integral at the limit of the sequence to actually work out the integral at the beginning of the whole setup. A fabulous application of analysis there. Got very algebraically heavy in the middle. Hopefully it wasn't too difficult to follow along, or at least you could take the hints and fill in the gaps yourself. Thank you very much for watching. Please do watch the rest of this playlist for the other questions within Step 2 2024.